So, an algebraic invariant for C-star algebras. So, so somehow the ultimate punchline of the talk is that there is an algebraic invariant that you can associate to C-star algebras. And this has enormous utility in various guises, and in particular here, we're looking at one specific application, which is has to do with the variety of spectral behavior that you can get in certain operators on Hilbert space. Okay, so told we're okay with C-star algebras, but I'm happy to go over it. Is that accurate or no? Yeah? Let's go over it. I can, and by the way, it's a ravage of age that my eyesight is poor, so these glasses are meant for reading this paper and this chalkboard. So if you're disgusted or irritated, you have to make a really enthusiastic face about it. Otherwise, I will not be able to tell. Right. So let's say that phi of H is Hilbert space. In this case, would be separable and infinite dimensional for the purposes of this talk. And this is continuous linear maps on H, equivalently bounded in the operator norm. Okay, and so bounded linear operators on H, where T is a map from H to H, and the norm T is the soup over all vectors, norm at once, one of the norm of T apply to X. So if this quantity is finite, then you have a bounded operator that's equivalent to being continuous. Right? So the concrete description of a C-star algebra then is that C-star algebra is a norm closed. Right, so this number, right, is the norm of T. So a C-star is a norm closed star subalgebra of B of H, where this star is just the adjoint operation, which is, the infinite dimensional analog of the complex conjugate transpose. So that is the concrete definition of a C-star algebra. Alternatively, and this is a theorem, you can say that a C-star algebra is a complex algebra, which is also a Banach algebra. So it has a norm, it's complete with respect to that norm, and it has an operation like the adjoint, an involution, a period 2 isometry that does all the things that the adjoint does, right? What that means then is that there are various examples of C-star algebras that are not explicitly presented as operators on a fixed Hilbert space, but which can nevertheless be realized as such. And so for a short warm-up list, you can take n by n matrices with complex entries. You can take, continuous functions vanishing at infinity on a locally compact Hausdorff space. And this, of course, is a commutative algebra, and this, in fact, is the totality of commutative C-star algebras by the theorem of Gelfand and Neinmark. And then you can start combining things like this. So you could take continuous functions from some compact Hausdorff space into the n by n matrices. C-star algebras admit things like inductive limits, so you can map one C-star algebra into another and another and another, and there is some nice universal limiting object. So that gives rise to things like approximately finite dimensional algebras. You can also associate, I'll just write it this way. There's a natural way to associate a C-star algebra to say you have some countable discrete group acting some compact metric space, then there's a nice way to associate a C-star algebra to that action. There's a way to associate a C-star algebra to just about anything. And then a question often becomes, how much does that C-star algebra reflect about the original object? So it's an interesting collection of objects. One of the first things you want to do with such a collection is you want to try in some way to classify them, to put them into various buckets. So I'll just mention, you know, I mean, at the inception of the study of algebras, of operators like this, that was the work of Murray and von Neumann in the 1930s. They studied things which were, in fact, not only closed in the norm, but also in the topology of pointwise convergence, which is somewhat weaker. Okay, and so, and those algebras are called von Neumann algebras, and in a sense, they represent a non-commutative expansion of measure theory, right? And so, Kohn and this was in the 1970s. They carried out the classification of, it's not important that we really know these words mean. I'll say it briefly. First thing you want to do is look at things that are somehow algebraically simple. A factor is a C-star algebra whose center is just multiples of the complex numbers, right? So somehow atomic in a certain sense. It's also closed in this topology of pointwise convergence in addition to norm convergence, so it's kind of a measure theoretic object. And amenable is, well, won't say too much about it other than it means it somehow comes from reality rather than things like the free group. But Kohn and Hagerup, this is, Kohn got the Fields Medal for this, and, Hagerup is the guy that Fields medalists call when they're out of ideas. And so they carried out this classification, and somehow when you allow your C-star algebra to be closed in the topology of pointwise convergence, not just the norm topology, which is sort of like uniform convergence, then things are easier, right? And then the question is there a nice classification of C-star algebras, right? So we don't necessarily allow closure in the topology of pointwise convergence, just norm closed. And this is a big and sort of amorphous question, right? And in general, you're going to have to impose some conditions. For any sort of reasonable answer, you need / start with you want to start with the simple objects, right? And most things are built from simple objects in some way. So we're going to ask for that. So we want simple. We're also going to want separable, just separable topologically. There's a countable dense subset. And then the last thing we need, in the spirit of what Kohn and Hagerup did, is that these should be amenable. And in the world of C-star algebras, this has a pretty nice interpretation. What it means roughly is that the C-star algebras are locally like matrix algebras. They have some degree of locally, they look a bit like this guy here. So can you do it? Is there some way to classify these things? And conjecture of Elliott of 1990. Yes, these are classified by, say this loosely because I'm trying to get toward this promise of an algebraic invariant. So what Elliott conjectured, based on some reasonable evidence at the time, was that these C-star algebras, simple, separable, and amenable, locally like matrices, could be classified. And all you needed to do that was K-theory, which is the appropriate notion of cohomology for these algebras, and traces. Traces are non-commutative measures, or integrals, more properly, right? So if you have a commutative C-star algebra, they all look like this. What is a trace? It's integration against some regular Borel, typically probability measure on X, okay? So a trace is, so if you keep track of the cohomology and the measures on the algebra, then that's enough to determine the algebra up to isomorphism. And for a long time, this held water. I mean, all of the natural examples we had, and indeed to this day, for the most part, the examples that come from natural situations like this one here, frequently satisfy this conjecture. Remarkably, I mean, the C-star algebra is determined entirely by cohomology. And in the case, for instance, of these group actions, what are the traces? They're exactly the invariant measures of the action. Okay? So, and yet no. So things were going well for a while until they weren't. What turned out to be the case is that most of the natural examples that we'd been considering accidentally had some degree of regularity, some degree of good behavior there that we hadn't noticed because everything was going so well. And so in the end, I mean, no means that you can find two of these simple, separable, amenable C-star algebras which have the same cohomology and have the same non-commutative integrals, and yet are not isomorphic, right? So these examples are distinguished by, and this is the algebraic invariant, the Kunz semigroup. And tell you what that is. Okay? So this will be my notation for it. Cu of, you put a C-star algebra here, and that'll be a semigroup. It's a ordered semigroup. It has a number of interesting extra properties, but where does it come from? Well, a little bit.
Can I maybe
Yes.
Just emphasize to some others in the audience that these aren't yet no.
Wow.
Just to provide some context.
Yeah. Actually, that reminds me, I forgot to make, since this is being recorded, I have to acknowledge the support of the Leverhulme Foundation. Was made possible Mr. Toad's wild ride through Europe for the next 6 months. So yes, and yet no. So where does this thing come from? And this is reasonably algebraic. So hopefully we all are comfortable with what a Hilbert space is. In the world of C-star algebras, you can expand this view a little bit. A Hilbert space has an inner product. That inner product takes values in the complex numbers. You can expand this view to Banach spaces where the inner product no longer takes values in complex numbers, but takes values in a C-star algebra itself, okay? So a Hilbert module over A, and this is a C-star algebra, is a Banach space with an A-valued And rather than agonize over all the specific details of the definition, I'm instead just going to give you some examples which will really cover everything that we're going to consider here today. So A itself, what is the inner product of A and B? It's the adjoint of B times A. That's it. Okay, so this makes a Hilbert module. Example 2, which is close to universal for the separable case, is little L2 of A, which is, a set of sequences. And these are square summable, okay? And the by virtue of the square summability, then the obvious kind of coordinate-wise inner product here produces the correct A-valued inner product. And then why is that example so important? So it's a theorem of Kasparov that if, say, M is a separable Hilbert A module, then M, of course, you can form the direct sum of Hilbert modules and more or less follow your nose way. And L2 of A is absorbing, in this sense, right? In other words, every countably generated or separable Hilbert A module lives naturally inside L2 of A in various ways, of course. Okay, so you've got these modules. The last thing I want to say is that these are connected to elements of the original C-star algebra A. These modules here, okay? Fact, theorem, however you'd like to think of it. So here's L2 of A. You can consider algebraically this curly K is going to be compact operators on genuine Hilbert space H, right? So these are, think of them as bi-infinite matrices that decay rather rapidly to 0 in all entries, right? And this tensor product, never mind what the details are, basically these are bi-infinite matrices whose entries are elements of A, which again decay rather rapidly to 0 in all directions, right? These guys then, this is probably the wrong notation, but act on can be thought of as operators on L2 of A in the same way that the compacts act on H, right? Just by multiplying, these are sequences of elements of A. These are matrices whose, giant matrices whose entries are from A. And you can just carry out the multiplication as you normally would, right? So with that view, every one of these modules M is actually equal to a fixed single positive operator in here. What does positive mean? It means positive in the same sense as an operator on Hilbert space, right? Eventually, you can take any C-star algebra and recognize it as operators on Hilbert space, and that's all we need. So they all look like this. So, yes. Yes. So this is a direct sum of Hilbert modules, and this isomorphism would be an isomorphism in that category. But in the same way that the compact operators act on Hilbert space, the tensor product of A with the compact operators acts on the sort of A version of Hilbert space, L2 of A. And the fact of the matter, thanks to Kasparov's theorem, et cetera, is that every one of those countably generated Hilbert modules looks like this. You just take some fixed positive operator and apply it to L2 of A and close it up. And there you go. Right? All right, so we've got these Hilbert modules, and I'm going to then, here comes the bane of my existence. Here's the part where I have to think of something to say while it dries, right? Or else forever smear the rest of the talk. So we're going to take these Hilbert modules and we're going to define an equivalence relation on them, which is, technically speaking, the equivalence relation is kind of picky and squidgy and annoying to define. But for the algebras I want to consider, and for the vast majority of C-star algebras that anyone is interested in, it just amounts to isomorphism, right? So for the purpose of today's talk, let's just say it's isomorphism. So that's what I'm going to do. I'm going to take the collection of all of these countably generated Hilbert A modules, whatever those really might be. You know, this is the productivity gap between America and Europe, right here. This is it. Forget what the economist told you. Okay, so the Kuhn semigroup of A, as a set at least, is equal to Hilbert modules modulo isomorphism. Okay, so a priori, that's just a set. You can show this is nice equivalence relation, whatnot. You can set, so like M, we'll use these square brackets to denote its equivalence class. Okay, then I'm going to define a sum on these classes. Will be the class of the sort of obvious direct sum of Hilbert modules. And this winds up being well defined ultimately due to Kasparov's theorem here. There's a way to make sure that this is okay. And we're also going to say that M less equal to N if and only if M isomorphic to M prime, which is a proper submodule of N. And so it's inclusion up to isomorphism. All right. So that's an algebraic invariant. It comes from algebraic objects. Where does K-theory come from? K-theory really comes from restricting your attention in this setup to the finitely generated and projective guys. That gives you the K0 group. This is a bigger world. This is all the countably generated ones. And for a long time, this was not relevant. Somehow, miraculously, we could understand everything about the structure of most naturally occurring C-star algebras using only the finitely generated and projective modules and recording what all the traces were, all these non-commutative integrals were. Then it turns out that there's more to it. So I'd like to pre-erase this other board, actually, while I talk. So give you a few basic examples of, that this is all very abstract. What does this thing look like? I guess I wanted to make it look algebraic, but in fact, this little fact here means that you can equally well define the Kunz semigroup as a kind of equivalence relation for positive operators. And that actually is the way that you get some nice examples, basic examples that will help you understand what this thing looks like for straightforward C-star algebras. So let me say then that this can be viewed as an equivalence relation on positive elements of via this, M corresponds to some kind of closed left module generated by A. Okay, so let's for now think of it that way. This is going to be an equivalence relation on positive elements. Let's consider first just the complex numbers. What is this thing, Cu of A? Well, Cu of A is just non-negative integers, okay? And how do I decide which non-negative integer, right? So I'm supposed to consider positive elements in the complex numbers tensored with the compact operators, right? In other words, I'm supposed to assign to every compact operator some non-negative integer. What is that integer? Whoops, I should have said. That integer is just the rank of the operator, right? I mean, there's two options for a positive operator. It's either finite rank, in which case it's got some number attached to it, or it's infinite rank, and that's it. Okay. So then you might hope, let's take another example. Let's take A is equal to C of X. Okay. Well, the news is both good and bad here. If you restrict your attention to positive elements which actually live in this algebra as opposed to in the tensor product with the compacts, then there's a very nice way to tell when two positive elements are equivalent in this strange sense, okay? So, two positive elements would be two functions on X that are greater than or equal to 0. When are they equivalent in this sense of Kunz? So they are equivalent in this sense if and only if they have the same support. And that would at least initially suggest that somehow the news is good for commutative C-star algebras, that this is an object you can get a handle on. And the reason that Elliott's theorem doesn't work is that nothing could be further from the truth. It is an unmitigated disaster. So what happens is that as soon as you allow tensoring with the compacts here, what this semigroup winds up recording is the K-theory of every possible closed subset of X in every possible orientation and intersection you could imagine. Is completely incomputable. I mean, it's like asking to compute the isomorphism classes of every vector bundle. I mean, what are all the vector bundles over every compact Hausdorff space of dimension at most 7? Good luck. I mean, it's not happening, right? And somehow the C-star algebra, all the C-star algebras we've been dealing with for a while, did not have this feature. Something happened in the simple C-star algebra that somehow destroyed this high-dimensional behavior. And it was a guy named Willitson who in the mid-90s gave the first examples of C-star algebras where somehow the horror show that happens for C of X persists in these simple C-star algebras, that this bad behavior persists. Okay, so that's the Kunst semigroup. That's roughly why it's relevant. But now I would like to switch gears entirely to a problem that, in fact, Karen and Bishan and I worked on 10 years ago, I guess, which is related to a super nice theorem we think we could all get behind. Not an example. Theorem. While, the word classical gets bandied around in this business a lot, but I think if the number starts with 18, you're good, right? Definitely classical, especially if you don't know what the other two numbers are, which I could look up, but Okay, so I was looking at the following problem. Let's say that A, B, Hermitian, n by n, complex matrices. With, and I'm going to list the eigenvalues in increasing order. Of course, there could be some repetition here. Say 801. Okay, you got two Hermitian matrices. They're therefore diagonalizable. They have a list of eigenvalues. And with repetition, these can be ordered in increasing order because they are real, right? The question Weil wanted to answer was, what he proved rather, is that the inf over u unitary of the norm of ua u star minus b, right? So if I allow conjugation by unitary, right, how close can I make one Hermitian operator to the other? Or in other words, how far apart are the unitary orbits of two Hermitian operators on finite dimensional Hilbert space? And what he proved was that this is the max I of the modulus of lambda I minus eta I, where it is certainly important that they have been ordered in increasing order, sometimes called the marriage lemma. Okay, so the answer is spectral, right? If you would like to know how far apart the unitary orbits of two of these operators are, then the answer lies in their spectra, and in particular in this funny distance. Okay, a very, very elaborate way of looking at the eigenvalues of two Hermitian operators is to say that they correspond to measures, and the measures in question are just the average of the Dirac mass at each of these points. Okay? So that's a fancy way of recording this information, which does not really seem to have any purpose. I mean, this is a much nicer way to state the theorem. But one thing that happens is that you can say that this distance over here, the answer to how far apart the unitary orbits are, is a distance between those two measures, which actually is a distance that has significant generalization to general probability measures, something called the Levy-Prokhorov distance between two, say, regular Borel probability measures on the interval. You can always reduce this question to the situation where A and B have norm 1 and where the spectrum is contained in the interval from 0 to 1. You can always do that. Anyway, so this is a classical result, and it's a full classification of unitary orbits of Hermitian operators on finite dimensional complex Hilbert space. Why? Because we know exactly when two such orbits are the same, thanks to this information here, but we also know what the full variety of orbits that occur is. Because if you give me a list, an increasing list of real numbers with repetition, I just write down the n by n matrix that has those along the diagonal, and there you have an example of a Hermitian operator that actually realizes that spectrum, right? So it's not even, it's sort of an afterthought. No one would consider that part of the theorem, okay? This kind of distance theorem is generalized to, and here I'll be a little brief, but basically the same idea that the distance between unitary orbits of self-adjoint operators can be determined spectrally holds water in lots of other situations. In the case of B of H, this is due to Azoff, Davis, just like 80 something. And then for, it's not important really, but von Neumann algebras, of which those factors I talked about at the very beginning of the talk are an example. You can do it there too. Spectral information tells the story, okay? This is due to David Sherman, somewhere around 2010-ish, okay?
I mean, there was some earlier work.
There's Hiei and Nakamura, and what did they do?
It was, I think, 2-1.
Maybe they did the 2-1 factors, and so yeah, I this is not an exhaustive list. I apologize, but started pacing over here. So what Ishan and Karen and I looked at was what about C-star algebras? What about if the ambient algebra is a C-star algebra? Can you say something similar? Are unitary orbits of positive operators in there determined spectrally? What about C-star algebras? Okay. Well, this is a pretty broad class. This C-star algebra, n by n matrices with complex entries, is evidently pretty well understood in very many ways, right? Same goes for B of H and von Neumann factors and von Neumann algebras, right? So it's unlikely, and in fact, it's sort of untrue. In fact, I'm pretty sure I can prove it's untrue that in general, you can have a spectral answer to the question of how far apart are two unitary orbits. However, you can get a decent answer. We restrict to nice C-star algebras. And what do I mean by that? They will be simple, unital, separable. These are not especially big asks. The big ask is that we should exclude that nasty phenomenon I discovered, that this kind of high-dimensional topological behavior can persist in a simple C-star algebra. We should restrict our attention to those C-star algebras for which Elliott's conjecture about classifying via K-theory and traces actually works. There's a very nice sort of conjectural characterization of what makes a C-star algebra amenable to that kind of classification. I don't want to get into the details of it. Suffice it to say that it's banishing high-dimensional, topologically high-dimensional behavior. But if you do that, and I'll just put it this way, classifiable sense of Elliott. And anyone who wants to ask about further details, I'm happy to give them. But this is the situation we're going to look at. Restrict nice C-star algebra, simple unital separable, and amenable to classification in the sense of Elliott. Includes all these cross products, includes inductive limits of finite dimensional algebras, and loads of other groupoid algebras. Great things in there. Okay, right? So what are these algebras? Where is this spectral information? So let's say we've got one of these C-star algebras, given A, and A in A, which is positive. And finally, given, I'm going to write it this way and tell you what it is. I've talked a little bit about this, a trace on A. I've said it's like a non-commutative integral. Given a trace on your C-star algebra A, how are we going to get spectral information? Here we are going to invoke one of the fundamental results of functional analysis, which in our situation says that if you look at, I'm going to take the C-star algebra generated by this positive element and the unit of the C-star algebra, right? So just all non-commutative polynomials in these two. In fact, it turns out to be commutative because it's all powers of A. It's a commutative C-star algebra, and this lovely theorem of Gelfand and Naimark says that in fact it must be then continuous functions on some compact Hausdorff space. Better than that, it's continuous functions precisely on the spectrum of A. So this is continuous functions on the spectrum of A, right? If you take the trace and you restrict it to this C-star algebra, commutative C-star algebra, every trace on a commutative C-star algebra is genuinely implemented by a measure. It really is integration against the Borel probability measure on the spectrum. It's the integral against a measure I'll call mu tau, right? So given a positive operator in there, every trace gives you a measure, gives you some spectral. So the information we get is not just what is the spectrum, but how is the spectrum weighted? And the thing that happens in the n by n matrices is that there's only one trace, and therefore there's only one way to weight the spectrum. But in the case of a general C-star algebra, every trace gives you a novel way to weight the spectrum of the C-star algebra, okay? So I'll call this mu tau A to indicate that it's connected both to the trace and to A, okay? And so what was proved with Karen and Bishan is the following. So given A, we get a map F. It takes traces to probability measures on the interval in exactly the manner I just described. Where does a trace go? It goes to the measure associated to that trace and that positive element. For every trace, there's a weighting of the spectrum of A, right? So you get, for every positive element, you get a continuous map from this. This is a lovely compact convex set, metrizable compact convex set. It's got an affine structure. This too has an affine structure. And this is a nice continuous affine map. Okay? We've got a map from traces. So this is like a spectral profile of A. It's telling you not only what the spectrum of A is, but how it's weighted with respect to every possible non-commutative integral. So we do this for two different positive elements, right? So the distance, the infimum over all u unitary, recall Weil's theorem of u, b, u star. What's the distance between two unitary orbits now in the spirit of Weil? It is sup over all traces of a distance between these induced measures. So for every fixed trace, you get a measure on the spectrum of A and a measure on the spectrum of B. You can consider those as being measures on the real line. You can compute this so-called Levy-Prokhorov distance between those measures, which is really, if you want, what is the Levy-Prokhorov distance? The intuition comes from Weil's theorem, right? It's just this marriage lemma distance between an average of Dirac measures, right? That sort of tells the story. Roughly, they assign kind of the, if two measures are close, then, you know, if you take an open set, they roughly assign about the same mass to that open set, right? And this tells you the distance between the unitary orbits of these two positive operators, okay? Yes?
Here,
Yes, please.
this is not all unitary from some ambient Hilbert space. This is just in C-star.
Right. Yeah, it's unitary in the C-star algebra A, right? Where, you know, a unitary operator on Hilbert space can be characterized either analytically by saying it's an isometry of Hilbert space, or it can be characterized algebraically by saying that u times its adjoint is equal to its adjoint times u is equal to the identity. It's that algebraic characterization that you can then carry over to an arbitrary C-star algebra, and those would be the unitary operators in the C-star algebra. So, yes, thank you.
I think you're saying these
Yes.
these two things are equal.
Yes, sorry. Equal to the sup of this. Yeah, pardon me.
So
I want to issue a small correction in terminology that we got wrong in the paper, actually.
Oh, okay.
So this was pointed out to me by Robert McCann when I was at U of T. He's this sort of
Oh,
name in
yeah.
optimal transport.
I hate that guy.
It it's not the Levy-Prokhorov distance. It's the infinity Wasserstein distance.
Infinity Wasserstein
There's
distance.
there's a small difference between the two. The Levy-Prokhorov distance has a plus r. You want the mu of u, the r enlargement plus r to be bigger than nu of u. This doesn't have this plus r apparent.
Oh, it doesn't. Okay, well.
So I mean, it's okay. It's just terminology, but it's kind of important terminology because this infinity Wasserstein distance is stronger than the weak star topology on measures in general. And whereas the Levy-Prokhorov distance gives you the weak star topology. That doesn't affect anything substantively.
Great.
I'm just saying it's something.
Good. I appreciate that. No. Don't distribute this widely. Yeah. Like the Epstein file. Chop that bit out. Right. But the answer is again spectral, right? Now I want to come back to what I said here, which was, okay, this gives you the distance between unitary orbits, and then there's also the question of existence. Is it true that for every finite increasing list of real numbers, there is a Hermitian operator with that spectrum? Well, yeah. I mean, that's easy, right? Now we've got a more complicated question. Is it true that for every suitably continuous affine function from the tracial state space into probability measures over here, there is a positive operator, little a, in the C-star algebra, such that the induced map from A actually is the original F you started with? That was sort of the missing piece. And that's where this Kunz semigroup comes in again, believe it or not. So.
sorry, one other thing.
Yeah.
In this theorem, we also need the
spectrum to be connected. Yes, yeah. You have an A and yeah. So, yeah, and I mean, somehow there is a Kuhn semigroup answer when the spectrum is not connected, but it gets sufficiently ugly that it's not really, you know, none of us is curing childhood cancer out here, right? So you got to remember to sell it, okay? Seriously. If I could give one piece of advice to any young mathematician, right? Sell it. Like the world of high-end art without the money and glamour. Which again is a salesmanship issue. Shit. Okay. So let me then ask this, that this is the question we want to answer. Question. Given F without getting into details, F will be continuous, affine, and it will be necessary, given the nature of our target algebra, that the probability measure, F of tau, is, I'm going to call it faithful. All I mean by this is that the measure of any open set is strictly bigger than 0, right? There's no dead spots in this measure, right? Can we find such that, what's the question? Such that the induced measure corresponding to a given trace for this element A, here it is over here, comes from the spectral theorem, right? Is equal to F of tau. Is that possible? And the answer is yes. Oh, how does that go? Maybe, let me not. And once again, as Bishan pointed out, the situation we're considering is the one where A has connected spectrum. The spectrum is the unit interval. Okay? So then, let me just erase this bit, not the rest of it. Step one here is that if you have a positive element here, and if we know this is really those continuous functions on the interval, then any positive element like this, these positive elements are in one-to-one correspondence with injective homomorphisms from this C-star algebra into A, right? So the A we are considering are in one-to-one correspondence with star monomorphisms. B sub A. Okay. So this is what we are looking for. Another way to view what we are looking for is the existence of a specific star monomorphism, which realizes some information that we have prescribed a priori, right? 2, I want to tell you what the Kuhn semigroups of this guy and this guy are. Because even though I told you that things get really horrible really fast, in fact, for nice C-star algebras, for these classifiable ones, they don't get horrible, right? And that's somehow how we got away with all this classification stuff for years, right? So the Kuhn semigroup of C01 is just the collection of all lower semi-continuous functions from 0, 1 into the naturals together with a point at infinity. How does that come about? Well, what am I supposed to consider here? I'm supposed to consider this thing tensor product with the compacts. You can recognize that object as just continuous maps from the interval into compact operators, right? So for every point in the interval, you get a compact operator. So for every point in the interval, you get a rank of that compact operator. And if you take some positive operator in this guy tensor of the compacts and you look at the rank at every point in the interval, that winds up being a lower semi-continuous function. And that's exactly this function over here. Everything is determined by the rank of the operator, okay? So it's a manageable object, lower semi-continuous functions into essentially natural numbers from the interval, okay? What about the target algebra? Well, write some letters and then wave my hands a little bit, but the second bit is semi-recognizable. The news for well-behaved C-star algebras, the ones for which Elliott's classification theorem works, is that this sort of thing kind of still holds, okay? What's this here? This V of A is called the Murray-von Neumann semigroup. All it is the finitely generated projective Hilbert modules, the thing that produces K-theory, okay? Positive elements come in two flavors. They're either equivalent to a projection or they're definitely not. And if they're definitely not, just as was done here, there's a way to calculate their rank with respect to every trace. In fact, I can tell you how it goes if you have A and A, it's greater or equal to 0, and you have a trace, then you can define this thing, d tau of A. I'm going to take the trace, not of A. Whoops, I'm going to take tau A is the limits over n. I'm not going to take the trace of A. Rather, I'm going to take the trace of its nth roots, right? If you have a diagonal matrix and all the entries on the diagonal are positive reals, non-negative reals, you can certainly take roots of this thing, right? And what will happen if you take roots of that thing, right? All the non-zero entries on the diagonal will converge to 1. All the zero entries will stay 0. If you then apply your standard trace to that limit, what you get back is the rank of the original operator, right? And that's the motivation for making this definition. So as fancy perhaps as it seems in general, this is just saying for every trace, there's a way to measure the rank of A, right? And so where do you get a function in here? Well, this is great. Given A and A greater than 0 trace, then A gets mapped to, let's call it G sub A. And G sub A at tau is equal to d tau of A. You just compute the rank of A at every trace, and that will give you some function on the trace space, which turns out to be nice, lower semi-continuous, affine, etc. Okay? So these are what the two Kunz semigroups look like, okay? And then the third ingredient is a marvelous theorem of Lionel Robert. Which says the following, roughly. I mean, this is not the full generality of the theorem, sort of simplifying it to our purpose, but given well, little gamma goes from the Kunz semigroup of C01, which I've just described, to the Kuhn semigroup of A, which I've just described, right? There exists star homomorphism, capital gamma, between the C-star algebras, such that, and this I've kind of been carrying and not saying all along, the Kuhn semigroup is not just an invariant, it's a functor, right? It takes not just objects to objects, but maps to maps. And so what Lionel proves is that morphisms at the level of the Kuhn semigroup lift to honest-to-goodness star homomorphisms, right? So basically, right, I want a star monomorphism. I want the punchline of this theorem here, right? And what I know is what these two Kuhn semigroups look like. And I've been given a piece of information. I've been given a continuous map from the traces into probability measures. And somehow with that piece of information, I have to cook up a map like this, apply Lionel's theorem to produce my star homomorphism, and then verify that that star homomorphism and the positive element to which it corresponds actually has preserved that initial piece of information, the continuous map from traces to probability measures. And that's exactly what happens in the end, right? But the essential intermediary is this Kuhn semigroup, which seems like, quite a departure. We've been talking a lot about just strictly analytic stuff, and somehow to realize this positive element now, you need to move into an object which is defined as isomorphism classes of modules over the C-star algebra. But the last thing I'd like to say, which I guess I'm out of time, I'll just say it really briefly. How do you define this? How do you define this map at the level of the Kuhn semigroup? So if, let's say, H belongs to lower semi-continuous functions from the interval into I need this Kuhn semigroup map. I need something at that level. So I have to say where this lower semi-continuous function goes to over here in this object. It's going to land in here, okay? So I have to tell you what little gamma of H is at a given trace tau, okay? And it is just going to be the integral of the function H against the measure corresponding to what was my initial piece of information, this function here, f of tau, d mu tau. Anyway, the story is told by integration. There's a lot to verify here. There's a lot I've swept under the rug about the Kuhn semigroup. It has a lot of algebraic structure that needs to be preserved that goes well beyond just the partial order and so on. But long story short, you can show that it is preserved and therefore that you have this lifting. And anyway, this completes the classification of these positive operators with connected spectrum in the well-behaved C-star algebras. Sorry for going over a little. Thank you very much.
Very much. Question, audience.
Yeah.
So,
Oh, Mike. Awesome.
So this works for classifiable, simple, separable,
Yes.
Your
Yeah.
side stable,
Nice.
stuff.
Yeah.
So outside of this, though, you have graph C-star algebras which are not classifiable, but can be classified if you know what I'm saying.
So not classifiable in the sense that they are not Z-stable?
I don't know what goes wrong.
Ah, okay.
Sure. So then you can put in extra stuff that I don't remember in order to fix that. And then with that larger set of invariants, they are classifiable.
Right.
With respect to that larger set of invariants, they're classifiable.
Uh-huh.
Would this work then in that setting?
My guess is that some version of it would work, but the invariant involved maybe can no longer be as simple as just the Kuhn semigroup of the two algebras involved, but some similarly enhanced take on the Kuhn semigroup that mirrors the enhancement that you need for the invariant of those algebras. I will say that if you leave the world of like genuinely classifiable, like non-Z stable or then I'm pretty sure I can show you that even the original thing about like how close together are unitary orbits or when are they the same fails catastrophically. I mean, the spectral information tells you nothing. So this is as good as it gets in some sense. You can go beyond nuclear with this. The only essential ingredients here really are, I mean, the essential ingredient for uniqueness is this property of strict comparison. But if you would like to do the existence thing, you also need this property of almost divisibility for the Kuhn semigroup. But I expect that there is some version of this, and frankly, I would be quite interested. I mean, one thing that would be nice to understand is, you know, to what extent you can extend this to inductive limits of matrices over interval algebras, and if there's anything interesting or meaningful that can be said there.
At the moment, I'm working on some sort of a non-commutative version of this, the uniqueness question. Computing distance between unitary orbits where the domain is, yeah, like a limit of dimension dropout.
Okay, good. So like a simple limit of dimension drops, and then what would the statement be somehow?
The statement would be, so if that's the domain, and you have two embeddings of this algebra into something that's very, very nice. I mean, classifiable and real rank 0 and compact finite dimensional boundaries. Then the two unitary orbits of these two embeddings can be computed in terms of distance between. Spectrum.
I mean, I think it's yeah. It's a fascinating problem. I mean,
but that does I mean, like, okay, that one generalization is kind of removing some restrictions on the codomain, but what about other kinds of spectra, like unitaries as opposed to?
yeah, I mean, I actually worked a little on that with a graduate student. So the question really is, what if instead of C01, I had continuous functions on the circle? And there, I think it should be doable, but I don't quite know how to do it yet. The idea, what would the engine for all of this at the end of the day is actually not even Lionel's theorem. It's this unreadable paper of George and Aline Ciperka, where they show that, you know, in stable rank 1 algebras somehow, that isomorphism of Hilbert modules is the same as Kuhn's equivalence, right? And it is critical in that case that when you look at just stable rank 1, that's it. And so what's critical in that case is that they, you know, this is my favorite picture in the world. This is a positive operator, C-star algebra. And so it's of norm 1. So it's the identity function in the C-star algebra it generates. And then they look at these little cut downs of it, right? And they have corresponding Kunz classes. Those are totally ordered, right? This guy is smaller than this guy, smaller than this guy. On the circle, that total order disappears, right? And so you're left with like bump functions that overlap, like fence posts. And you need to quantify, you know, what does it mean to almost have a circle? In terms of, you want an algebraic definition. I have the following Kunz classes. They sum up to the unit. They have the property that they're indexed, and if their indices are far apart, you can find orthogonal representatives. And, you know, they have some overlap. Basically, whatever you would expect if you drew the circle and then just started drawing bump functions on it, right? And that seems challenging. I mean, I think it can be done, but But you would not, I mean, then there's the question of how you manage to hit the correct K1 class. I mean,
But in a follow-up paper, 2 hours that Fahrenheit with Aleph and Yati.
yeah.
Yeah, we address unitaries in particular, but in certain special cases, for example, assuming that the K1 of the embedding is true.
Right, okay. Yeah, so then yeah, I don't know how to target a particular,
Right.
unitary.
Yeah, indeed, that's a separate question. which
Yeah.
I'm also.
Yeah. I mean, so, I don't know. But, yeah.
That's this thing, and for example.